Okay, so one of the sections that we did not formally cover, it was section 11.7, maximum and minimum values. Now this section, there's a problem in MATLAB assignment number 5, an exercise that deals with maximum and minimum values. And it comes from section 11.7, and it deals with a test called the second derivatives test. So I want to just go over this briefly because you're going to be using MATLAB to help you do the second derivatives test. Okay, so let me just talk about this briefly. So in figure 1 here, you can see a surface, function of two variables, x and y, and you can see this surface has maxima and minima. And how would we, how would we identify, what criteria could be used to identify a maxima or a minima of a surface? Well, first, just like in calculus 1, you have to find a critical point, right? You have to find a critical point. Okay, well, what does a critical point mean when you have a function of two variables? Well, let me show you what that means. Here's what it means. If a function has a local maximum or minimum at a point AB, then the first order partial derivatives of the function exist there, and those partial derivatives are both equal to 0. So if you think about it, if you look at the picture here, anytime you are at a maximum, for instance, if you were to take a tangent line in the direction of the x-axis and a tangent line in the direction of the y-axis, both those tangent lines, if they're touching the top there of the hill, those tangent lines would have to be flat, right? They'd have to be horizontal, right? So at a maximum, the two tangent lines, one going in the x direction along the x-axis, or I should say in the direction of the x-axis, and the other tangent line going in the direction of the y-axis, if we were to sit those tangent lines at the maximum there at the top of the hill, okay, those tangent lines would have slopes of 0. And similarly, for a minimum, those two tangent lines would also have slopes of 0. Now, does that make sense? Think of like taking two rulers and sitting the rulers on top of the maximum there. The rulers will balance nicely at the maximum point, but they're going to be horizontal. Okay, each will be horizontal, having a flat slope or a slope of 0. All right, are there any questions on that? And the same for the minimum. All right, who's feeling comfortable with that? Who's reasonably comfortable with that that geometric explanation? All right, Hyunwoo's good. And Ellie's good. Excellent, excellent. Well, okay, and Juliana's good. Excellent, excellent. So then that leads then to this Fermat's theorem. Fermat's theorem says that if you have a function that has a local maximum or minimum at AB, then the partial derivatives with respect to x and y will equal 0. Okay, and that's absolutely true. Okay. Okay, so therefore we have a way that we can find critical points. But then the next step is, once you find your critical points that's where the surface has a maxima or a minima, the next step, of course, is to determine whether the maxima or minima, well, you have your critical points, but you got to determine if the critical points represent a maxima, a minima, or neither. Okay, so, and this is called the second derivatives test. So the second derivatives test is proven in the back of your textbook. We're just gonna, you're just gonna take it on faith here, but you can look at the proof in the back. But there is some intuitive feel here. Like for instance, if you were to have, so criterion A and B, they say if this directional derivative D, this D, which is, hold on, D is the product of the second partial derivatives with respect to x and y minus the mixed partial derivative squared. Okay, so in part A there, that's highlighted, it says the second partial derivative with respect to x is greater than 0. So that means with respect to the surface in the x direction at the point AB, if you look at the concavity of the surface in the x direction, in the direction of the x-axis at the point AB, would the surface be concave up or concave down? It would be concave up. That's right. That's right. And so if you have a situation, right, where, let me just maybe show you here real quick. If you have a situation where you have a surface and it's concave up, okay, and the tangent line, let's say that's the tangent line in the direction of the x-axis, that's flat. Okay, that's flat, so that is a slope of 0. Well, at this point here, why is that a maximum? Well, think about the concavity. The concavity. Hold on now. Wait. Oh no, I'm saying this wrong. I'm actually doing part B here. Let me go back to the, well, no. Let me go back to the thing here. I said this wrong. Let me go back to the thing. One moment. Okay, so we're on part A. If the second part, so if D is greater than 0, and the second partial derivative of f with respect to x at AB is greater than 0, then you have a local minimum. If the second partial derivative of f with respect to x is greater than 0, then is in the direction of the x-axis at the point AB, is the surface function f of xy, is that concave up or concave down if the second derivative there is greater than 0? Is it concave up or concave down? Hold on here. It is concave up. That's right, Gunu. So this makes perfect sense, because if you have a function, okay, like this, and this is clearly looks to be a minimum, right? And incidentally, we can we know that the tangent line, hold on here, let me just, horizontal tangent line in the direction of the x-axis is flat. Okay, so this is a critical point. That red point is a critical point, right? But it is a minimum because your function, hold on, your function f of xy is concave up. Okay, it's concave up. Okay, so at AB there, the partial derivative second partial derivative with respect to x at AB is greater than 0. So, I mean, intuitively, this makes sense then. This makes sense. If we go back to the second derivatives test now, that part A, you know, I mean, I'm not saying that, you know, the directional derivative, you know, that's proven in the back, but certainly it makes sense that where the surface is concave up, if there is a critical point, that critical point would be a minimum. And similarly for part B, if you have a situation where directional derivative is greater, or the second derivative test gives you d greater than 0, and a second partial derivative of f at the critical point is less than 0, well, when the second partial derivative of f with respect to x is less than 0, what's that tell you about concavity? Is it concave up or concave down? Is the surface concave up or concave down at the critical point? It's concave down. That's right. And so if we, you know, again, go to the whiteboard, you know, there's a function, okay, flat tangent line there. So what is this point AB? Well, it's going to have to represent a local maximum, because your function, well, that's the function, but the second partial derivative with respect to x at the point, the critical point, in this case, is less than 0. Okay, and so you have a local maximum at that critical point. And this is exactly what part D says. All right, this is helping you give you a little feel for the second derivatives test. Okay, okay, I'll take that, kinda, yes, all right, good, Juliana, excellent, Charles, so good. And now the third case is, what if the second derivatives test, okay, gives you a d less than 0? Okay, well then the function isn't a maximum or a minimum. Okay, so basically you have this situation like you have in figure 3. So in figure 3, that saddle looks like a saddle. At the bottom of the saddle, okay, you can see that if you look with respect to the y direction, okay, where the saddle's flat, okay, there, okay, in that groove, okay, with respect to the y direction, looking with respect to the y-axis, is that critical point a maxima or minima? In figure 3. It's a minimum. That's right. Good, Hunu. But if you look now in the direction of the positive x-axis, okay, and you know when I say look in the direction of the axis, I'm always talking the positive axis, you know, in the positive direction on the axis. With respect to the x-axis, does it seem like the surface has a maxima or minima there? A maximum, that's right. That's right, Ellie. Okay, so If you're moving in the positive x direction, you have to climb up to get to that critical point. But if you're moving in the positive y direction, you slide down to get to the critical point. So that point is called a saddle point. It's neither a local maxima or a local minima. Yeah, well, that's right, Ellie. When you have functions of two variables, you can have a critical point where it is neither a maxima or a minima. That's right. It can be what's called a saddle point, and that's what you have there in Figure 3. That's called a saddle point. Okay. Are there any questions on that? All right, Ellie, you're good? You're comfortable? Good, good. So of course, like what's normally done, like if we look at an example here, where they want you in example 3 to classify critical points of the function given by x to the 4th plus y to the 4th minus 4 times x times y plus 1. First, you locate the critical points by setting the two partial derivatives equal to 0, right? Well, you find the two partial derivatives, and then you set them both equal to 0. That gives you two equations and two unknowns. Now you solve for x and y. And this is where, if like this is kind of a beautiful problem, everything's going to work out fine, and you're going to be able to determine your critical points, okay? Basically, you can solve if you let the first equation, if you let y equals x cubed, you can substitute that in the second equation, and if you do that, you're going to end up getting an equation in x, and this is what you're going to get. Okay, this is what you're going to get. You're going to get 0 equals x to the 9th minus x, and that can be, believe it or not, it can be factored, and you can find roots. You can find roots. So see, they factor it at the end, as far as they can factor it. X to the 9th minus x equals x times x squared minus 1 times x squared plus 1 times x to the 4th plus 1. But the only real zeros, real roots, come from the x and the x squared minus 1. And so x equals 0, x equals 1, and negative 1 are the three x values for the critical points. And if you substitute them in back into the other equation, you'll determine the corresponding y values. Okay? So this is a problem that worked out very nicely. But, of course, many problems don't work out nicely. But nevertheless, you can use, you remember like Newton's method in Calculus 1 could be used to find roots of polynomials. How many recall that? Well, you used it. I'm trying to recall. Hold on here. Okay, I had a thumbs up on that. Good. What I'm trying to say, let me just say it the right way. Okay, yeah, well, so Newton's method, Newton's method was back in Calculus 1, okay, and it was a way to find the roots of a polynomial equation, okay? So, there is a similar technique that can find so like a zeros of a polynomial function with respect to x. But, you can find, like this problem, it worked out well. It worked out fine to substitute in, like when you had these two, hold on here. When you had those two equations, you were able to solve for the first equation, y equals x cubed, and then substitute in the second equation, and it worked out. But you're not always able to do that. So there are programs where you can find critical points without like there are algorithms that are programmed, subroutines, algorithms that can find these critical points. And then once you find them, they do it numerically, kind of like Newton's method is used to numerically find a zero of a polynomial, or zeros of a polynomial. It's the same kind of principle. And again, I hope we're limited in time on the course, but I hope to show you maybe in a later class a MATLAB program that will do that. Maybe even for this particular example, I can show you. But to understand, what it means for a critical point for a function of two variables, we have to discuss what we're discussing now. And the second derivatives test is valuable because it would still be used to determine if you have a maxima or minima, even if you had a program that could find the critical points. That being said, you'll notice in this example, hold on one moment. In this example 3, we're looking at example 3 here, that once they find the critical points, okay, they go ahead and apply the second derivatives test. Okay, so there's the D used in the second derivatives test, and you see below how they establish they compute the second partial derivatives at 0, 0, at 1, 1, and at negative 1, negative 1, and from there they're able to establish whether those points yield minima, maxima, or saddle points. And it turns out that this particular problem, that for the points negative 1, negative 1, and the point hold on here, 1, 1, you have local minima, and then at the point 0, 0, since the second derivatives test is at 0, 0, d of 0, 0 is negative 16, that is going to be a saddle point. And they have a nice picture here that shows you the actual surface, okay, and you can see it has two minima and it has a saddle point, okay? So if we now go into the MATLAB assignments, okay, so again, if you let me just hold on here. One moment. Okay, so if you go into the MATLAB assignments and then click the red here, the second one, you can see MATLAB assignments 4, 5, and 6. And for this particular problem, or this MATLAB assignment, let me bring it up separately. So you can download it, right? Let me just find it. One moment. We're looking right for MATLAB assignment 5, right? So let me get it here. One moment, everybody. One moment here. Okay, so MATLAB assignment 5 deals with, it's titled gradients, okay? And you know something about gradients, right? And as you know, there are nice illustrative examples But this particular, you know, I mean, basically what you're going to be doing is you're going to be using gradients to determine if a function has a maxima or minima at a critical point. And, you know, you can look over the illustrative examples but A and B deal with the gradient approach, okay, like example 1, well, there's like, I want to say it's the right way, like if you go down to, let me see, it's page 1, 2, yeah, if you go to page 3, it says use the second derivatives test to classify the critical points of that function. And here they show you how to program in the second derivatives test in MATLAB. Okay, and they work through a nice example here. Okay, and I'll let you look at the code. They talk about vectorization and so forth. They're able to find critical points, and in the end, and I'm going to let you look that over. Okay, but in the end, they, you know, with the code, you can find the critical numbers. You know, and then in the end of this little illustrative example, they tell what the critical numbers are, and they have it in a nice format, and then they apply the second derivatives test. But the one thing that isn't done is they don't mention at each critical point whether it's a maxima or a minima or a saddle point. And so you have to remember to do that when you do the exercise that says use the second derivatives test. So if we go down a little bit here, this MATLAB assignment number 5 has two exercises. But the first one says use the second derivatives test to right here. Yeah, use the second derivatives test to classify the critical points. So when you classify the critical points, you don't just stop, you know, here, right? Based on the second derivatives test, for each of those points, you ought to be able to say whether the critical point is a maxima or minima or a saddle point. So don't forget to do that in your write-up, okay? All right. Are there? So this MATLAB assignment 5 has two exercises that go with it, and I just wanted to, you know, the second exercise talks about using simultaneous contour and gradient plots near the critical points to help you identify whether the critical point is a maxima or minima or a saddle point. And I think you'll be fine on that. But the second derivatives test, I just want to talk about that a little bit so that you'll be a little more comfortable with this exercise right there, the first one. Are there any questions? Okay, I'll stop the recording, and I will include this recording along with the MATLAB assignment number 5. Okay, I'll put it with it. So, okay, great.